Let's go through the practice exam and see why the solutions are what they are. So here's the first question. I was surprised when I gave this question last semester that a lot of people had some difficulty with it. You're just analyzing this formula here, which describes how the length of an object changes as its speed approaches the speed of light. And I think what a lot of people found confusing about it is that it contains a lot of constants. So this L0 here is just the original length. This is the original length of the object. And okay, so actually that's the only, and the speed of light. So this is the speed of light squared. Squared. And the first thing you have to do, you can see here, question A is to find the limit as the velocity of the object approaches the speed of light from below. Of course, it has to approach the speed of light from below, right? Because you can't go faster than the speed of light, so there's no way to approach it from above. So velocity of this object is approaching the speed of light from below, and you're supposed to evaluate the limit as v goes to c. Alright, well remember that our favorite way to evaluate a limit is just to plug in whenever possible. And there's actually no reason not to plug in right here. So if you just plug c into this formula, you get that L is equal to L0, whatever that is, times the square root of 1 over c squared, or 1 minus c squared divided by c squared. And so what is that? That's L0 times the square root of 1 minus 1 is L0 times 0 equals 0. Alright, so as the speed of an object approaches the speed of light, this formula is saying that its length approaches 0. So surprising but true. So if you see something like a physical equation, what you need to do is just pretend like everything that's not the variable is just some fixed number. This L0 is just some fixed number like 12 inches. And c is the speed of light, which is 300 kilometers per second or something. It doesn't matter, it's just a number, it's going to stay there. And so you can replace it with any other number, and the same thing will happen as the velocity increases, because those numbers are just fixed. Alright, so let's look at, I think we've really already done this whole problem. So B says, as the velocity of an object increases, does its length relative to stationary observer increase, decrease, or stay the same? And we just saw that as the object's velocity increases, this formula is telling us that its length goes to 0. So the answer to part B is decrease. And C says, why is a left-hand limit necessary? And so then there's this snide joke. I can't believe I put an emoticon on an exam. It says, your answer should be mathematical, not philosophical. So the philosophical reason that the left-hand limit is necessary is because you can't go faster than the speed of light. So of course it must approach the speed of light from the left. But there's a mathematical reason too, and I explain that down here in my solution to part C. So if velocity were ever greater than the speed of light, then you would have a negative number under the radical. And if you have a negative number under the radical, then the function's not defined. So that function, for the way length changes as a function of velocity, just isn't defined if v is greater than c. So the domain is from like 0 to c. Okay, so that's the mathematical reason. And that's the solution to the first question.